Last week, I was sitting in a drafty community center basement, listening to a local city planner drone on about load balancing and the rolling brownouts scheduled for the coming summer. It was the usual rhetoric of the old, world-fragile grids, aging copper, and the need for collective belt-tightening. In the back row, I noticed a guy who looked like he'd been living in a server room for 3 days straight. He wasn't nodding along, he was smirking, scrolling through a logistics manifest on a ruggedized tablet. When the planner mentioned that a new data center nearby might have to wait 5 years just for a permit to upgrade its transformer, the guy actually laughed out loud. He leaned over and whispered, "They think we're still plugged into their wall." He showed me a satellite photo of a nondescript industrial lot out in the high desert. No power lines coming in, just a cluster of sleek modular containment units that looked more like spacecraft than buildings. "That's 2 gigawatts of deep fission," he said, his eyes practically glowing with a kind of post-human calm. "We're not waiting for the grid anymore. We're the grid." He talked about atoms and bits, as if they were the same substance, explaining how he'd just spent the month converting a defunct Bitcoin line into a fortress of H100 GPUs. To him, the city planner's concerns about sustainability were like a candle maker complaining about the light bulb, irrelevant and slightly tragic. He wasn't just building a company, he was engineering an exit strategy from the 20th century. But then, I asked him what happens when the regulators catch up, when the AI safety boards start knocking on his door to talk about guardrails. The smirk vanished instantly. His face didn't just turn serious, it went cold. He didn't argue about policy or law. He just looked at me and said, "Every hour they delay us is a statistical murder. While they debate ethics, people are dying of old age and the species is rotting on a single planet." That sharp pivot, from the smug confidence of a man holding a private nuclear sun to the raw, almost religious fury at any hand that would pull the throttle back, was jarring. It made me realize that for people like him, 2025 isn't just another year on the calendar. It's the year they stop asking for permission to build the future. Okay, so let's unpack this. That opening narrative, it just perfectly captures the central conflict we're diving into today.
It really does.
Yeah.
It's the friction, right? The friction between this aging, centralized, sort of bureaucratic energy system.
And the urgent, decentralized demands of, 21st century technology.
Exactly. We're talking about a need for energy superabundance to power the massive, and escalating compute requirements of advanced AI.
Right. So our mission here is to take a deep dive into the actual market data, the regulatory changes, the financing figures, all of it. We want to see if this exit strategy the server guy was bragging about is real.
To see if using advanced nuclear technology, specifically small modular reactors or SMRs and these deep fission concepts, if it's actually moving from a PowerPoint slide to, concrete and steel.
And doing it outside of the traditional grid structure. That's the key.
And what's fascinating is that the urgency in your story, it's completely reflected in the global market realities. We are so far past the point of a gentle energy transition.
It's not gentle anymore.
No. The global system is undergoing a profound transformation, and it's driven by this rapidly growing electricity demand. And not just in the West, but especially across the global South.
And that demand, coupled with the need for resilient low-carbon power, that's the accelerator.
It is. It's precisely what has pushed SMRs from being this, distant innovation on the horizon to becoming market-ready, first-of-a-kind infrastructure projects, FO8 projects.
Okay, let's pause on that term, first-of-a-kind, because I think that's critical. It sounds important, but it also sounds risky. We hear SMRs are market-ready, but what does FOC really imply in this context?
That's a great question, and it's where the money meets the metal, so to speak. First of a kind means that while the technology itself is proven, the first commercial unit of a specific design, it carries these unique financial risks.
Risks related to what? Manufacturing.
Manufacturing learning curves, regulatory delays, unforeseen construction costs, you name it. Historically, if you look at large nuclear projects, they almost always had massive cost overruns on that initial build.
Right.
So SMR developers are trying to manage that FOAK risk, and they're doing it aggressively. It's why we're seeing so much private financing and these government matching grants. They're essentially sharing the cost of the first few builds.
So they can get past that initial hurdle.
Exactly. So they can rapidly transition to standardized factory-built units.
That makes perfect sense. Absorb the R&D cost of the first model to pave the way for cheaper, mass-produced versions down the line.
Yeah.
But what's really accelerating this push, is it just the economic need for digitalization, or is there something bigger, maybe a little darker, at play?
I'd say it's both, but the geopolitical driver, energy security, is completely dominant right now. I mean, if you look back, the 1970s oil shocks triggered the first huge build-out of commercial nuclear power across Europe and North America.
A direct response to a supply crisis.
Precisely. And now, fast forward to today. The 2022 disruption of Russian gas exposed the exact same global vulnerabilities to imported energy. It created a similar, very acute strategic imperative.
So energy security is back on top of the agenda.
It's a core national policy goal driving SMR adoption in a way that just aiming for, carbon targets alone never could.
So countries aren't just looking for clean power.
No, not at all.
Yeah.
They're looking for reliable,
domestically controllable power.
Exactly. And SMRs, because they're smaller, quicker to deploy.
And scalable.
Right. They fit that strategic need far better than waiting, 2 decades for some huge 10-gigawatt plant that requires this massive upfront capital.
This really gets back to that idea of resilience. The problem with a lot of the current grids, especially with heavy renewables, is intermittency.
Absolutely. That intermittency means you have to rely on backup gas or very expensive short-duration battery storage. Yeah. SMRs offer what is really the only path to 247 low-carbon power that is domestically sourced and isn't vulnerable to, say, pipeline politics or extreme weather events.
Okay, let's go back to the central theme here. Bypassing the old world.
Mm-hmm.
You mentioned the data on site ownership, which feels like the most concrete evidence we have that this private grid is actually forming. Mm-hmm. Who's making the investments? Who's building outside of that utility comfort zone?
This is where we see the market really start to fracture.
Yeah.
Traditionally, utilities and governments were the only players. They were the only owners of nuclear assets.
Right.
The NEA SMR dashboard tracks these global ownership plans. And yes, the majority, about 49 sites, are still linked to traditional utilities or government bodies. Another 14 are linked to national labs for research and demonstration.
Right.
But the real signal of disruption is in the 11 sites explicitly connected to private industrial players.
11 sites. That might not sound like a huge number compared to 49, but that's a foundational shift. That's private industry deciding they literally cannot wait for the public grid.
It's the ultimate expression of that exit strategy. The data shows that these private entities are specifically seeking clean, reliable power and high-temperature heat. Things the legacy grid often can't provide reliably or, crucially, quickly enough.
And you said the U.S. is leading this.
The United States, mostly because of its decentralized energy structure and that aggressive venture capital environment, shows the greatest diversity in site ownership. It's the non-traditional stakeholders who are really leading the charge.
You mentioned industrial heat and off-grid power. Can you give us some color on that? What are these non-utility customers actually planning to do? Why do they need nuclear heat so badly?
Well, these new markets are very specific and often way more profitable than just selling bulk electricity to homes. A major area is industrial process heat.
For things like manufacturing.
Exactly. Heavy industries, think chemicals, cement, steel production, they need extremely high temperatures, far higher than a conventional reactor can provide. But these new generation 5E designs, like high-temperature gas reactors or HTGRs, they can provide steam or heat up to, say, 750 to 950 degrees Celsius.
Wow.
So industrial partners are driving the demand for this heat because it allows them to decarbonize their manufacturing without compromising their output.
That is a fascinating application.
Yeah.
You're using nuclear not just for electrons, but for direct heat to power the hardest to abate sectors of the economy.
Exactly right. And another critical market is off-grid power for remote sites. Think mining operations.
Okay.
If you replace the diesel generators at a remote mine with a small containerized nuclear reactor, you solve 2 enormous problems. First, the vast expense and the security risk of constantly trucking fuel into the middle of nowhere.
And
Second, you eliminate the massive carbon footprint associated with mining. So these are high-value use cases that offer immediate superior returns compared to just traditional grid supply.
This really confirms that the private sector is investing based on these niche, high-value demands, not just broad public utility needs. But I have to ask, the data shows they're building, but does it show they're building faster than the traditional utility sector? The city planner in the opening was stuck on 5-year permits. Is the private sector really leapfrogging that bureaucracy?
That is a crucial point of friction, and the answer is a bit complex. The private sector is definitely moving more aggressively in its technology choices and deployment commitments.
They still have to deal with regulators.
They do. They still have to navigate the national regulatory bodies. However, their primary advantage isn't necessarily speed in permitting, but it's speed in financing and site selection.
How so?
They choose sites designed around their specific needs, often right next to their industrial clusters. This allows them to completely bypass the complex, highly politicized grid interconnection and transmission approval processes that just bog down utilities for years.
They're co-locating.
By focusing on co-location, they eliminate the need for high-voltage transmission entirely.
That is the essence of the exit strategy, just eliminating dependencies. And this isn't just happening in a few large economies, right? You mentioned global momentum.
No, the global momentum is what validates SMRs as a tool for energy democratization. We're seeing over 30 countries developing their first ever commercial nuclear projects.
30 countries.
And these are often nations that just can't financially or logistically support a massive 1,200 megawatt traditional reactor. SMRs, being smaller, under 300 megawatt, are a perfect fit for their lower electricity demands or constrained financial resources.
And I saw that there's a new kind of diplomatic infrastructure being built around this tech. What does that international collaboration look like on the ground?
It looks like a rapid build-out of political and technical agreements, all designed to streamline SMR adoption. I mean, take Poland, for instance. They want to start their first plant by 2036.
Ambitious.
Very. And to do it, they've signed cooperation agreements with Canada, France, and the US. They're essentially ensuring they can pull technical expertise and financing from multiple global leaders.
So they're hedging their bets.
And beyond that, you have this Japan-US initiative that's created a multinational framework. They're collaborating with countries as diverse as Ghana, Kazakhstan, the Philippines, Ukraine. It's not just technology transfer. It's about embedding shared energy policy and security interests across different continents.
So private developers are getting in on this too.
Absolutely. You see Korea's KHNP. They've contracted with Uganda for a site study for their first potential SMR project. It just proves that SMRs are becoming the global baseline for any country looking to get into nuclear for the first time.
Okay, that gives us a really firm grasp of the why global security, private demand, geopolitical necessity. Let's move to section 2 and really focus on the engine of this revolution, the technical velocity and how regulators are responding to this acceleration.
Right. And when we talk about velocity, the data on pre-licensing activities is just, it's striking.
What does it show?
It's the concrete proof that regulators are finally recognizing the urgency of the market. The massive scale of regulatory activity is astonishing. Over 33 SMR designs began pre-licensing activities globally.
Okay, but what makes that number so critical is the change over time, right?
That's it. It represents a 65% increase from the previous year. That dramatic jump tells you that regulators, after years of deliberation, are now in a responsive, forward-leaning mode. They're desperately trying to keep up with the pace of private innovation.
65%. That is not incremental change. That is an institutional scramble. It sounds like the pressure from the private sector and these national policy goals has finally broken through the typical inertia you see at a nuclear regulatory body.
It signals a maturation of the entire sector, and we're seeing tangible regulatory breakthroughs because of it. In the US, for example, the nuclear regulator granted construction licenses for 2 non-traditional generation baby designs.
And those were?
Kairos Power's Hermes and Natural Resources MSR1, both are molten salt-cooled concepts.
Licensing a generation Davy reactor, this feels like a huge technical and psychological leap compared to the traditional water-cooled designs we're all familiar with. Why is molten salt cooling such a big deal? What does this signal?
It signals a profound shift because molten salt reactors operate in a fundamentally different way. Traditional reactors rely on extremely high pressure to keep the water coolant from boiling.
And they have complex mechanical systems to manage the heat.
Right. Molten salt reactors, on the other hand, operate at atmospheric pressure. They're designed to exploit passive safety features. If the system overheats, the fuel literally just drains into a passively cooled containment tank.
So by licensing these, the regulators are embracing a different safety philosophy.
Exactly. They're embracing inherent passive safety, moving away from a reliance on highly complex active engineering safety systems. And that is a key selling point for SMRs.
That has to reduce the construction complexity and the potential failure modes significantly. So while the U.S. is licensing these advanced designs, what's happening elsewhere? Are others already in operation?
They are. China's high-temperature reactor pebble bed module, the HTRPM, achieved commercial operation in December 2023.
And that's a gas-cooled reactor, another Gen V design.
Right, proving that these different non-light water concepts are moving past the demonstration phase. And separately, Russia's KLT-40S floating SMR has been operational since 2022. So the deployment status varies by country, but the global takeaway is clear. The technology is no longer abstract. It is operating in a commercial capacity right now.
Let's delve a little deeper into that technical diversity, these deep fission concepts that really embody the server guy's vision of a self-contained power core. The diversity is just staggering.
The current wave of SMR development is absolutely defined by this diversity. We're moving so far past the traditional reliance on water-cooled reactors.
Like the Niscale design.
Right. The generation of steepy concepts being pursued now include, well, 5 major types. You have water-cooled, which is still relevant, but highly engineered for safety and modularity.
Then gas-cooled.
Gas-cooled, which uses inert gases like helium. That's crucial for providing the extremely high temperatures, up to 950 Celsius, needed for industrial heat and highly efficient electricity generation.
Metal-cooled.
Middle-cooled, using liquid metals like sodium or lead. They offer superior heat transfer efficiency, which leads to smaller cores and better use of fuel. TerraPower's Natrium is a key example there.
Then molten salt-cooled, which we just discussed.
Right, inherently passively safe, low pressure. And then the 5th category is heat pipe-cooled, like Radiant Industries' Kaleidos reactor.
Okay, let's focus on that last one. Heat pipe-cooled. What is the technical advantage there? It sounds almost like science fiction.
It is the ultimate expression of simplicity and modularity. These reactors use sealed metallic pipes filled with a working fluid, like sodium. That fluid vaporizes to transfer heat from the core, and then it condenses, flowing back to the core.
So it's a completely passive system.
Completely. It requires no pumps, no moving parts, and no complex external plumbing for core cooling. This design is exceptionally attractive for remote, off-grid, and even mobile applications, because the reactor can just operate entirely on its own.
Which means it can be deployed rapidly with minimal maintenance infrastructure. Perfect for that industrial lot in the high desert you mentioned. This flexibility is what enables the exit strategy. We're tracking land-based, marine-based, and critically mobile concepts.
The drive for mobility is very real. The U.S. Department of Defense's Project Pele is the most famous example, aiming for a small, transportable microreactor. But we also see companies like Mobile Nuclear Energy developing concepts like the MN1.
And that mobility just dramatically lowers the deployment timeline and cost.
Because it decouples reactor construction from site preparation.
Yeah.
You build it in a factory, and you truck the finished unit to the site.
This technical flexibility leads us right back to the data center market, which we identified as the single biggest driver of this whole private build-out. And there's a perfect case study, the Deep Fission Borehole Reactor, or DFBR-1.
The DFBR-1 is a prime example of customizing nuclear tech for private, high-security compute demand. It's a 50-megawatt thermal pressurized water SMR, but its key innovation is the deployment model. It's designed to be underground, borehole deployed. Putting it underground offers inherent security, simplified decommissioning, and a minimal surface footprint.
Okay, wait. 50 milliW thermal. We need to be clear about the distinction between thermal output, MWs, and electric output, MW. How much electricity does 50 milliW actually generate?
That's a crucial distinction. MLOF measures the heat from the fission reaction, while MW measures the net electrical power delivered to the customer. For a modern SMR, the efficiency conversion is typically around 30 to 35%.
So a 50 milliW reactor is generating somewhere between 15 and 17 milliW. It's a microreactor.
Exactly. It's ideal for a single large facility or a remote site.
Understood. A microreactor concept built for security and a minimal footprint. But the truly disruptive part is the commercial commitment it unlocked. This is what validates the entire opening story.
Absolutely. The crucial step was the binding partnership Deep Fission secured in January 2025 with Endeavor Energy. And this was not a non-binding letter of intent. This was a firm contract.
A contract to do what?
To co-develop up to 2 gigawatts electric of nuclear power. This capacity is specifically dedicated to supplying electricity to Endeavor Energy's data centers.
2 gigawatts. Amway. That is an exponential leap from the 15 MeV microreactor model we just talked about. How are they planning to achieve that scale?
They do it through the SMR concept of multi-module deployment. They leverage those economies of multiples. The 2G way is a multi-site, multi-unit deployment strategy. They'll use the standardized DFBR design, built repeatedly and rapidly across Endeavor's various data center campuses.
That commitment is the highest signal you can get. The private compute sector sees advanced nuclear as its primary immediate power source.
It is staggering. So let's transition into Section 3 and explore this intimate coupling atoms and bits and really understand why AI demand is forcing this nuclear build-out. A commitment of that scale shows this is not a niche market anymore.
No, AI is fundamentally transforming the requirements of energy supply.
That's because AI is consuming power like no technology before it. The sources we're looking at frame AI as the most consequential general-purpose technology since electricity or the internet itself. And while we often focus on AI's output, we have to focus on its resource alignment.
The inputs.
The inputs. Training and running these massive transformer models requires colossal, uninterrupted, and highly dense power.
We often hear that AI is a huge consumer of energy, but you're saying it's also part of the solution for energy production.
It absolutely is. And this is the fascinating feedback loop. AI's capabilities are perfectly aligned with solving the most complex challenges in the energy sector. It can discern subtle patterns in material science that accelerate the R&D cycle for reactor components and advanced fuels.
It can optimize things we couldn't before.
Exactly. It can optimize complex systems that were previously too difficult for traditional methods, everything from core fluid dynamics to real-time grid forecasting. So AI needs SMRs for power, but AI also makes SMR deployment faster and safer.
A self-reinforcing acceleration loop. But let's stay on the demand side for a moment. This massive compute appetite is why data center developers are bypassing utilities.
The demand signal is just overwhelming. The NEA dashboard explicitly identifies on-grid reliable power for data centers as one of the 6 near-term markets making real progress.
Then data centers don't just need power.
They need high-density, uninterruptible, 247 power. Any interruption can corrupt a complex, hours-long training run, leading to millions of dollars in losses. The traditional grid's instability is simply incompatible with the business model of hyperscale AI compute.
Let's look at the commercial scale examples, because they really illustrate the scale of this private revolution. We covered the Deep Fission and Endeavor 2 GWE deal. What other major collaborations are out there?
The commitments are unprecedented. I mean, consider the Oklo Switch agreement. Oklo, a developer of microscale metal-cooled reactors, signed a collaboration agreement with Switch, a major data center development company.
And their goal is
to develop, construct, and operate what they call Aurora powerhouses to provide up to 12 gigawatt of power across the U.S.
12 gigawatts. Just to give the listeners some context here, that's roughly the capacity of 10 to 12 large traditional nuclear reactors. It's enough power to supply a major U.S. metropolitan area like New York City or Los Angeles.
And this is being contracted by a private data center company, not a massive federal utility.
That is the scale of the disruption. The sheer audacity of a tech firm committing to a 12 GWA power solution. It just validates the server guy's vision entirely.
And there's more. We see Kairos Power, the molten salt developer, signing a power purchase agreement, a PPA, with Google for up to 500 milliwatt. When you have Google and Amazon, who led the X-energy race, moving this decisively, it confirms that the largest technology firms see advanced nuclear as the necessary power core for their immediate future, not some speculative long-term goal.
It confirms they're moving much faster than that 5-year transformer permit. But this begs the question, if the demand is so huge, why SMRs? Why not just revive the plans for those massive 12 GWE traditional reactors that utilities use to build? What makes SMRs the ideal surgical tool for co-location?
It all comes down to the logistics and the environmental footprint required for a modern, decentralized compute infrastructure. Data centers need to be near fiber hubs, away from population centers, and rapidly scalable. SMRs offer 3 key logistical advantages that traditional reactors just can't match.
Okay, what's the first one?
Firstly, the small physical footprint. Nuclear energy already has one of the smallest land use requirements of any low-carbon source. SMRs compress this even further.
And because they're co-located.
Because they are modular and co-located near the demand center, they eliminate the most complex and contentious part of energy deployment, building high-voltage transmission lines. You don't need new rights-of-way, which can take a decade of legal battles.
They are truly plugged into their own wall, just like he said. That proximity solves a colossal planning and logistical hurdle. Transmission is the choke point for the old grid.
The second advantage is water conservation. Traditional light water reactors require massive amounts of water for their cooling towers.
And data centers are often built in arid regions.
Exactly. It's an irony. They're in high desert regions due to cheaper land and better security, which just exacerbates water scarcity issues. But many advanced SMR designs use significantly less water. And crucially, generation Lafitte gas-cooled and metal-cooled concepts can use what's called the Brayton cycle for power generation.
Okay, we need to explain the Brayton cycle simply. Why does it matter for water?
Think of the Brayton cycle like a jet engine. Instead of heating water to create steam to turn a turbine, which requires vast amounts of cooling water to condense the steam back into liquid, the Brayton cycle heats an inert gas, like helium, which directly spins the turbine.
So it's a closed loop with gas.
It's a fully enclosed system. It uses gas, so it consumes virtually no water on site. This makes these advanced SMRs perfectly suited for those water-scarce, high desert regions that are so popular for massive data center campuses.
That is a massive strategic advantage for any high compute deployment in the American West or similar arid regions globally.
And finally, there's the critical minerals advantage, which is crucial for long-term supply chain resilience.
Compared to what? Batteries.
Compared to competing distributed solutions like massive battery arrays or large-scale wind and solar farms, SMRs are far less dependent on critical minerals like lithium, cobalt, or rare earth elements. The primary critical minerals they need, copper, nickel, and chromium, are standard industrial commodities.
Which de-risks the supply chain from the geopolitical volatility we see in the mineral markets. So SMRs provide the trifecta: minimal land footprint, minimal water use in the advanced designs, and a stable supply chain for the construction materials. That explains why they're the preferred tool. So we've established the need with AI demand, the technology with Gen IV diversity, and the market pull with these huge PPA commitments.
Wait.
Now let's tackle the hard reality of scaling this up. Section 4, the economics, and the key bottlenecks that could trip up this ambitious exit strategy.
This is the phase where the ambition of the vision hits the logistical reality of mass manufacturing. The traditional nuclear industry, it always relied on economies of scale.
Making reactors physically larger and larger to reduce the cost per megawatt.
Right. SMRs flip this paradigm entirely. They introduce economies of multiples.
That's a powerful distinction. How exactly does the economies of multiples model fundamentally change nuclear construction?
It shifts the focus from building a unique site-specific monolith to, well, serial production. It's basically applying Henry Ford's principles to fission. The cost savings come not from size, but from the repeated, standardized construction of modules in a factory setting.
A controlled environment.
A factory environment allows for stricter quality control, reduced labor costs due to specialization, and you leverage accumulated experience. The 10th module is far cheaper and faster to build than the first one.
And standardization must also reduce the regulatory risk.
Hugely. A design license once doesn't need to be relicensed repeatedly for every new installation. That ability to standardize the design and the regulatory process is perhaps the biggest lever for cost reduction.
But that model relies entirely on massive, committed upfront financing to build those factories. Has the private capital actually arrived to support this shift?
It has arrived in force, and it shows institutional confidence in the scalability of this model. The data is very clear. 10 SMR designs have secured $500 million or more in public announcements or financing.
And this isn't just seed money.
No, this is serious institutional capital betting on successful serial deployment.
So let's detail where this capital is coming from. It's not just government checks.
No, we're seeing a critical hybrid financing model. First, you have the publicly traded players, Niscale, Oklo, and Nano Nuclear Energy. They've collectively raised approximately $975 million via public markets, like SPACs and IPOs. That provides transparency and a direct route for private investment.
And the second part?
Second, the private venture capital involvement is staggering, and it's driven by the technology and users themselves. X-Energy secured a massive $700 million Series C1 capital raise led by Amazon.
Amazon. So Amazon isn't just a power customer. It's now a strategic investor in its own future energy supply.
The moment Amazon invests $700 million into a nuclear company, the conversation shifts entirely. It's a vote of confidence that transcends a typical power purchase agreement. It is the ultimate signal that the tech sector is internalizing its energy infrastructure.
And what about Europe?
In Europe, a company called Nucleo raised over $570 million, which marks the largest private effort in advanced nuclear on the continent. They're focusing on developing reactors that can run on existing spent fuel.
And government commitment is still important for that FOA risk.
Absolutely essential.
Yep.
TerraPower's Natrium project, for example, secured $1.98 billion in U.S. DOE matching grants. This public-private partnership is essential for overcoming the initial high barriers of regulatory compliance and manufacturing setup.
Okay, financing is only half the battle. Building physical reactors requires a mature, robust supply chain. Are these companies moving past paper agreements, past memoranda of understanding to binding manufacturing and procurement contracts?
They are. They're moving decisively into the procurement phase, which is a major signal of supply chain maturity. We're tracking progress through binding contracts, joint ventures, and in-house capabilities designed to secure these specialized components.
Can you give us some concrete evidence of this procurement? What are they actually ordering?
Take the Natrium project. TerraPower has completed procurement selection for all long-lead items for the Natrium reactor plant.
What does long-lead items mean?
It means placing firm orders for the specialized, high-quality metal components that often take years to manufacture. Things like the reactor vessels and specialized heat exchangers. They're working with world-class partners like Bechtel for engineering and construction, and heavy fabrication specialists like HD Hyundai and Doosan Enerbility.
So when the specialized forging for the reactor core is ordered, construction is imminent.
That is the physical reality coming together. And NuScale, being the most advanced water-cooled SMR, must have an equally mature supply chain.
You would assume so.
They do. NuScale has a highly mature supply chain. They're leveraging agreements with the EPC giant Fluor Corporation and have contracts with Doosan for forging upper reactor pressure vessels. They're securing specialized materials, like agreements with Alema for steam generator tubes. This movement from design to detailed material procurement shows a shift from theoretical engineering to actual manufacturing production line setup.
Okay, so we've covered finance and manufacturing. Now we have to discuss the throttle point. The one thing that, according to the data, could slow down this entire aggressive deployment schedule. What is the single biggest bottleneck?
The primary constraint for SMR deployment is the availability and reliable supply of highly enriched low-assay uranium, or HALEU. This is fuel that's enriched between 5% and 20%.
Why is HALEU the bottleneck? Traditional commercial reactors use LEU low-enriched uranium, which is less than 5% enrichment. Is the processing difference really that dramatic?
It is. The existing global enrichment infrastructure is geared almost entirely toward LEU production. The higher enrichment of HALEU is necessary for these generation FOIV SMRs because it allows them to achieve a much more compact core size, which is critical for modularity.
And it allows for longer refueling cycles.
Extremely long refueling cycles, sometimes up to 20 years. That makes them ideal for secure remote deployment without constant servicing. The problem is that more than half of the SMR designs currently under development, 39 designs to be exact, require enrichment above 5%.
And crucially, where does the world currently get its HALEU from? Or even its baseline enrichment capacity?
This is where the geopolitical risk really intensifies. The global commercial enrichment market is currently heavily reliant on Russia, which controls a significant portion of the world's commercial enrichment capacity.
So for the U.S. and its allies to deploy SMRs at scale for energy security and AI power,
they must break this dependency. They have to establish a reliable domestic HALEU supply chain. This makes the private efforts to secure fuel an urgent matter of national strategic policy.
That adds a profound layer of urgency to the exit strategy. It's not just about bypassing the grid, it's about bypassing a geopolitical dependency. So how are developers mitigating this fuel constraint given the scarcity and the geopolitical risks?
There are two main, highly aggressive mitigation efforts underway. The first is private fabrication and vertical integration.
Meaning they're building it themselves?
Exactly. Recognizing that dependence on external suppliers is a fatal risk, developers are investing heavily in their own in-house TRISO fuel production facilities. TRISO is the highly durable coated fuel particle often required for these advanced gas-cooled reactors.
And what are the key examples of this private fabrication race?
Well, X-Energy is actively constructing its TRISO X fuel fabrication facility in Oak Ridge, Tennessee. Kairos Power is advancing TRISO fuel manufacturing at its labs in New Mexico. Even in Europe, companies like Jimmy Energy are moving fast, submitting a license application to build a TRISO facility in France. These are capital-intensive efforts designed to guarantee a fuel source and eliminate that HALEU bottleneck.
That shows an incredible degree of vertical integration building the reactor and the fuel supply chain at the same time. What's the second mitigation effort?
The second is source innovation. This means securing HALEU from non-traditional stockpiles or recycling existing spent fuel. It's a highly resourceful, almost scavenger-like approach.
Tell us about those non-traditional sources.
The U.S. Department of Defense's microreactor, Project Pele, will use HLEU that's produced by downblending existing highly enriched uranium, or HEU, stockpiles from the National Nuclear Security Administration.
So they're taking weapons-grade or naval reactor fuel and watering it down.
Essentially, yes.
Yeah.
HEU is greater than 20% enriched. Downblending it to HLEU levels, which is under 20%, is a technical way to create an immediate domestic fuel source without waiting for new commercial enrichment facilities to come online.
And what about recycling?
Similarly, Oklo's Aurora powerhouse will get its HALEU by processing used fuel from the Experimental Breeder Reactor 2, a historic demonstration program managed by Idaho National Laboratory. This effort leverages existing government materials and recycling programs, bypassing the nascent commercial HALEU enrichment market entirely, at least in the short term.
This just demonstrates that aggressive urgency. They are not waiting for the infrastructure to be built. They are leveraging government stockpiles and recycling existing materials. This ability to be operationally ready by any means necessary perfectly reflects the mentality of that tech visionary in the opening.
And that operational readiness is enabled by key players. A company called BWX Technologies, which is fabricating Project Pele, owns the only privately licensed U.S. facilities that can perform that HEU downblending work. That unique capability makes them a strategic player in solving the HALEU bottleneck for the entire sector.
So they're ensuring the fuel can be sourced domestically and reliably.
Exactly. The fuel cycle remains the technical constraint, but the investments being made right now are attempting to widen that flow exponentially.
This has been an incredibly detailed deep dive that has truly mapped the current reality of this nuclear renaissance. We started with the anecdotal frustration of the old world planner and the defiant confidence of the tech visionary building his private nuclear sun.
And we've now validated that vision with concrete data, with financing figures, and the geopolitical context.
We have clearly mapped the convergence, the technological capacity to build this high-energy, high-compute future. It's not theoretical, it's being realized through binding partnerships and massive private capital.
And the regulatory speed has jumped by 65%. We see a dedicated effort to decentralize power, to optimize the smallest footprint for co-location with data centers, eliminating grid vulnerability.
The physical infrastructure, the atoms, is accelerating at a breakneck speed, supported by billions in private and public funds. And that is enabling the exponential scaling of compute, the bits.
In terms of civilizational development, what the data confirms is that the technological capacity for this attempt at Kardashev-type civilization scaling, the ability to utilize all the energy incident on a planet, is being realized outside of traditional structures. The technical hurdles, from generation of vis diversity to HALEU sourcing, are being overcome with radical ingenuity and massive financial commitment.
Which brings us back one last time to that jarring final comment from the character in the basement. Every hour they delay us is a statistical murder. He wasn't talking about technology anymore. He was talking about institutional speed and inertia.
And that is the central tension of this new energy era. It's no longer a question of can they build it. The stark conflict now is between the accelerating velocity of physical technology, the atoms and the bits, and the necessary but often slower evolution of the human systems, the governance, the regulatory bodies tasked with managing that power. The technological foundation for a high-energy future is here. The question is whether our infrastructure for social permission can possibly keep pace with our infrastructure for power generation.